The problem we're presented with is that there's an infinite number of gains we can select for this P controller, so which one is going to be the best one? We don't want to just keep trying random values of K until we find one that we like, because the value of gain that we choose is impacting the performance of our controller, that peak time, that max overshoot, etc. So one method for choosing a K from this infinite number of possibilities is the root locus. So basically what it's going to do is graphically show us how different gains are going to affect the behavior of our system. And really what we're looking at is all of the possible dominant poles or complex conjugate poles that we can have in our closed loop system. So it's going to graphically show us all the ones we can select from, and then we're going to be able to see what gain is going to get us to that specific pole location. Now, this is going to be applicable to systems that are not second order, as we're going to see, because remembering back to the end of Unit 2 when we're talking about second order systems and higher order systems like third order or when we have an extra 0 in our system, the behavior of the system was largely determined by what we call the dominant poles, or that complex conjugate pair. Then we saw if we had a third real pole that there might be a slight or significant difference in the max overshoot and the peak time depending on where that third pole was located. Same thing with a 0 in the system. There could be a slight modification to the baseline system or a major modification. So the root locus is looking at the dominant pole placement. And we know that if we know where that complex conjugate pair of poles are, that determines the natural frequency, that determines the damping ratio, those things determine the performance of our system. Now, when we look at a root locus plot, really what we're seeing is where the poles can be placed based on the curve of the root locus, and the pole graphically is going to be located on the plot, and the distance it is from the origin is going to tell us the natural frequency, which we already know because the absolute value or the magnitude of our poles or eigenvalues was the natural frequency. And the angle of the pole is going to tell us about the damping ratio in the system. Now, before going forward with the root locus, I do want to offer a warning or a caveat here. This is only one way that we can approach controller design. There's a whole host of other ways that are more modern, maybe more appropriate depending on the controller that we're using. But this does provide us some analytic framework for our controller design. Not that we necessarily need to use an analytic method. There are numeric methods or minimization methods we could use where we don't need to know beforehand what the equation is going to be. And a major drawback of using the root locus is that we're treating all closed loop controllers like they are going to behave as a second order system. However, that's not the case because we are often going to have 3 or 4 poles in the system. We might have a 0 or not in the system that the root locus is not going to be compensating for. It's always designing based on the baseline system, and the actual performance of the controller is going to be modified from there, and we're not predicting that beforehand. The other thing we're not going to be considering when we're using the root locus method is anything about the input. We're not going to know beforehand analytically what the peak input is going to be or what the total input or control effort that we call it is going to be. That's not considered in this method. So it's going to give us kind of a basic idea sometimes for our design, and we might need to refine our design based on what this initial root locus method is going to get us. So with that being said, root locus is often a useful first step, but as we get into more complicated controllers, it's not going to get us all the way there. We might need to use a hybrid method where we start with a root locus and then maybe use a numerical method or some trial and error from there. So let's look at the basics of the root locus method. Really what we're doing is we're taking the denominator of our closed loop transfer function, which is always that 1 plus kg expression, and we're setting it equal to 0. And what we're going to do is solve for any value of k, what are the s's that make that true? So really what we're looking at is we pick a k and we find the poles for that particular k, and then we're going to plot them on our graph. We then modify the value of k, find the new poles. So what we're going to be doing, or really what MATLAB or some numerical system is going to do for us, is solve for a whole collection of poles based on a whole collection of k values, because we're going to vary k from, well, by default, k to infinity, or we can zoom in on k values that we want to try as we're making our root locus. So MATLAB can make the root locus for us by using this rlocus command. So we're going to give it the system we want to make the root locus of, and then as a second argument, we can put in specific values of k or a range of k values we want it to use, or we can leave that blank and it's going to use the defaults. Now a little bit about the notation, or what system are we actually putting in the root locus. We are not putting in the closed loop transfer function, and we're not putting in necessarily the open loop transfer function. So what we do is we're going to put in this g prime, I'm going to call it, or GRL I'll sometimes use, and that's equal to the transfer function of our controller times the open loop transfer function, or plant. Now, what we don't include is the gain that we're putting into our controller. So we're going to see in a couple of slides, using it with a P controller or PD later, the G sub C does not include the K value, because that's the point of the root locus, is we're going to be selecting that K value. So we're going to see, like for a P controller, the GC is really just 1. And we'll see that in our example in a moment. So we never include the gain in this G prime or GRL. That is what we are going to be finding. So what the root locus is going to show us is all the poles we can select from and what gain will get us there. If there's a specific pole we want, and we'll see why that might be the case in a little bit, if it's not on the root locus, there's no gain that we can possibly choose that's going to get that pole. And again, what the root locus is always showing us are the dominant poles of our closed loop system. So if our closed loop system actually has 3 poles or 4 poles, we are only going on the root locus going to see the dominant ones, that complex conjugate pair that's going to establish the baseline system.